Okay, so this is a lecture that I neglected to discuss about back when I recorded the lectures for this course. So I think it would be a good time, or it's high time, since I just sort of, I guess, understood for real what modular arithmetic is. So let's talk about that, and let's talk about cyclic groups. So we've played with a bunch of structures that are common in mathematics, such as the ring, of course. We've played with the ring. I think we also discussed the module. We've also discussed or used topological spaces. Also vector spaces. And I also believe that we also used manifolds. Yeah, I know manifolds are a subset of topological spaces, but it's worth emphasizing that we played around with manifolds. In fact, I think I will make another video that will give you guys an update on some more structures that we have constructed, or I have constructed at least, from F, and some more interpretations of what exactly F is, because thus far we don't really have a concrete, we don't have a really complete and concrete definition for F. It's sort of a vague notion, or a very general notion. So I suppose that's the goal of these next few update videos, is to sort of give you guys an update. So okay, let's talk about the reason why I sort of wanted to make a video about this is that I just sort of understood, or like fully understand what modular arithmetic is. And it was because I was trying to understand what tensor products are and tensor sums, and it so happens, or the Wikipedia page, or at least my sources, explained or told me right out of the blue that Z mod 6, so Z mod 6, so the integers mod 6 is equivalent to the direct sum of 0 and 2, I believe, and 0, 2, and 4. Now, the reason why this is the case is because, alright, when we take the direct sum of these guys, we add, these two elements to each of these elements. So 0 plus 2 plus 0 is just 2. 0 plus 2 is 4. 0 plus 2 plus 4, I think we also missed 3. There's also 3, yeah, there's 3 in there. The order doesn't matter. Okay, so 0 plus 2 plus 3 is 5, so it's still an element of it, because this is all just equal to all integers from 0 to 0 to 5. 0, 1, 2, 3, 4, and 5. And note that these aren't just the numbers themselves, the one that you guys know of, like, 1 of something, 2 of something. Think of these as symbols right now. Okay, so, right. 0, 1, 2, 3, 4, 5. Once you get to 6, we wrap back to 0. That's how modular arithmetic works. I know it's a very intuitive notion. Frankly, I admit it's kind of stupid that I didn't understand it until now. But here it is. So I'll give you the gist of it, or this means. Okay, so essentially what we're saying is that this is sort of, I guess you could say, isomorphic to this over here. If this is some group and then this is a group, these two are completely isomorphic, or just isomorphic, or, well, if they're just sets, they're completely equivalent, right? And the reason why is because, all right, add these two to 0, we get 2. Add these 2 to 4, we get 6, which means we're back to 0, so 0 is part already covered. Add this to 3 gives us 5, and yeah, I think I'm missing something. Yeah, well, either way, you guys get the idea on why I stumbled upon like actually relearning modular arithmetic. It seemed like a very unintuitive topic, but now I got the, I guess I got it. So this is just of why we're doing this lecture, or this footnote. So yeah, this is going to be a footnote. It's not a full-fledged lecture. Any serious mathematician would realize that these lectures are actually incredibly incomplete. There are a bunch of stuff that we have not skimmed over, or that we definitely skimmed over, and we didn't care to even talk about. Perhaps even especially in position theory, what with tensor products, direct sums as well. Because, yeah, but I'll make a footnote for that another time. Okay. So today we're going to be focusing on modular arithmetic. What exactly is modular arithmetic? So, the same way you guys know that regular, numbers or regular numbers, 1, 2, 3, 4, 5, 6, or whatever number you think of, maybe 1 plus 1i, 1 plus 2i, 1 plus 3i, maybe even rational numbers 1/2, 1/4, 1/6, etc., etc. Modular arithmetic is a system which gives us a rigorous notion, or at least a mathematically sound notion of wrapping around. So you can think about a clock. So I'm just going to use a circle, and then I'm going to put tick marks to indicate this number here is 0, which is also equivalent to 12. 12 is just 0 mod 12. Okay. And then this is 3. 3, 6, and then 9. 1, 2, 3, 4, 5, 6, 7, 9. Okay, I need to write that. Okay, so right now, let's say that our arm is at 3 o'clock. And then, let's say we added, let's say we added 12 R's, right? Let's say we added 12 R's or 11 R's. So that gives us 13. So we're at R13. Now, we don't have a 13 here, but notice that we can express all of these guys. We can express all numbers, all possible numbers that are beyond 12 as being, just themselves, or equivalent at least, or congruent, that we use this symbol to denote it, as congruent to, well, their current position on the clock mod 12 here. So 13, the position of 13 on the clock is supposed to be, okay, 12 is midnight, and it's here. This is 12, and then 12, 13. So at 1 o'clock, 1 o'clock is 13, but this is just 1 o'clock. It's just 1, and then there's 2, and then there's 3. So how to express that? So we say that 13 is congruent, or it's in a sense similar, like how groups are isomorphic, or spaces are homeomorphic, or how curves are homotopic. 13 is congruent to 1 mod 12. And we enclose this in parentheses because we don't want to confuse this with the modulo operator, which is, well, this is not equal to 1% 12. So it's not equal to this, but in a sense, it sort of also encapsulates this idea of a modulo operator, because you'll notice that 0 congruent to 12 mod 12 is, it sort of makes sense, because you'll notice that 12 divided by 12 gives us 1. But there is no remainder. So that means the remainder is 0. And you notice that when we divide 1 and 12, our remainder is exactly 13. Now, because our remainder here is 0, that means we have no remainder. So, to better formalize the notion of modular arithmetic, we say that A is congruent to some B mod n greater than 1, for n greater than 1, if and only if there exists a k. So I'm gonna write this over here. If and only if there exists a k such that a minus b is equal to k times n. Because if I were to put it to words, we could say that two integers a and b are said to be congruent modulo n if n is a divisor of their difference. So a minus b can be divided by n with no remainder. So this doesn't have a remainder. So a minus b over n, no remainder. And if you guys don't know your division, a quick refresher, remainder is just the number that you get if you end up with a division wherein not everything is divided out. So an uneven division will yield some remainder. Like say 1 divided by 3 would give us just a remainder of, I suppose, 1, still 1. Or 4 divided by 3 is remainder 1 as well. So a minus b over n has no remainder. And I know, how does this relate to group theory? You guys will see in a moment, that any set, which I call A, mod some n, if A here is composed of integers, mod n, this is actually just isomorphic to the additive group of z mod nz. This is just notation, by the way. This is just this is equal, not equal. This is equal to z, the integers mod n. Okay. So I carried over this notion to person theory, which is generally a more general form of Femboy theory. Femboy theory, if you think of Femboy theory as the abstract algebra, you can see the person theory is the category theory of it all. So it's a more general form of the Femboy. So yeah. Okay. So here's a very important relation. If we treat f as a set of course, a fundamental set of all Femboys, it's what we defined to be at the beginning of this course. Right, so if we treat all of these Femboys, or if we assign every Femboy here with an integer, we would see, or we would show, or we can show that f mod n is isomorphic, or the additive group of this. So I could say this equipped with addition is isomorphic to z mod n. With additive group of the z n, which is isomorphic to the cyclic group Cn. Cyclic group of order n. Actually, it's the other way around. It's the cyclic order, or it's the cyclic group of order n that is isomorphic to the additive group of the integers modulo n. So I guess this is the theorem that we want to prove today. We want to show that there is an isomorphism between this and this. And frankly, we don't need to go into the weeds of, the precise and rigorous definition of an isomorphism. All we need to do is show that there is a bijection between this set and this set. In fact, let's not just do that, but let's show that there is an exact bijection between f, the space of all femboys, and the integers exactly. Now the integers over here is countably infinite. So it's not like R where in between two steps we would have an infinite amount of numbers. Here we have discrete steps that move on to infinity. Even though it's infinite or unbounded, it is still you can say countably, or it's countable. So we can still count on off to infinity, even though it would take an infinite amount of time to count all the integers. So yeah, we need to find a bijection between these two. And once we have that bijection, of course, it would preserve some structure at least, but nonetheless, f already has at least some structure to z. Now, one way of showing that f is somewhat akin to z is first putting it into correspondence with the natural numbers, and then sort of constructing z from that that equivalence. But that's something we're gonna explore for another footnote. So for this one here, what is our isomorphism between I suppose f and z for the integers? Now it's as simple, the isomorphism is as simple as corresponding every femboy with a respective integer. So using person theory, generalizing in person theory, if I have an indexed set of people or persons, or if I have a p-space containing I amounts, or well, containing let's say n amounts of people, I here is indexed by set j, and of course the cardinality of j would be equal to n. All we have to do is say that this is equivalent under our predefined isomorphism, which I will call mathcal L. Now, the reason why I pick L is I'm going to show you guys later. Okay, so we're going to correspond this p sub I to an integer I. So I is an element of z. And yeah, it's as simple as that. That's our isomorphism. Now you may be thinking, oh well, what about the inverse? What about the inverse? What if we want to map an integer I to a corresponding person, p sub I? What if we want to take I to p sub I under a hypothetical L to the minus 1? Well, it's simple. Just correspond it with a p sub I. Let's say for some person p sub 3, so a third person, the third person in our p space, its corresponding integer under this this map is just precisely 3. So it is listed as the third person. Yeah, so there is at least some ordering, or there is a notion of ordering when we correspond these two, because corresponding every person here and equivalently corresponding every femboy in an F space with an integer or a number in general in an ordered set, because Z has a total ordering. We can compare numbers from inside it. It implies that there is some, especially when we're saying that it is equivalent. So since it's an equivalence class, we carry some structure, or we carry over some structure from here onto here. So if this has some total ordering and we put it into correspondence with this set, then that means that this may also have some total ordering. So this would imply that some Pn is comparable. So we use this symbol to some Pn. So we use this symbol. I mean, it could be like this, but I'm gonna use this, and we use this to say that Pn and Pm are comparable. And M are, of course, not the same. but nonetheless they dictate some sort of order because under MathCal our transformation or our isomorphism, these guys are correspond to the respective integers n and m, and n and m are, you know, obviously comparable because they are both integers. Now we are not saying that Pn and Pm are or already have total order. It is only when we do correspond the space they're in to the integers via an isomorphism, it is only then that we say that there is some notion of total ordering between these guys. Okay, so right. So that's one thing an isomorphism must do. So we already have, you know, ordering here, so it carries over order. So we can say that from p to the minus 1 is less than p0, or the empty person. We denote the empty person like this, of course, because according to our isomorphism, L, it's corresponding to minus 1, and minus 1 is strictly less than 0, obviously. Now, if you want me to show that indeed one is less than the other, we can do that in foundations, with, you know, constructing the integers from the natural numbers. It's simple. It's just as simple as showing that, well, n is comparable, so therefore, because we constructed z from n, we carry on, or we carry over some structure from n, and that includes comparability, because n is also a totally ordered set, and because n is a totally ordered set, z, which is constructed from it, must be also totally ordered. Obviously, otherwise we won't have a notion of saying that one integer is less than the other, and thus we won't be able to tell if, let's say, a polynomial, right? Because polynomials mostly, at least, have integer powers, right? We won't be able to differentiate some polynomials with the other, like say x squared and x cubed. We won't be able to compare them to, or say that one has higher degree than the other, if we have no sense of comparability with the set that we take 2 and 3 from. So yeah, that's why we need this to exist, or that's why this must be a fundamental thing for the integers and natural numbers, and perhaps even the real numbers. Now the real numbers can be constructed simply from the natural numbers by, you know, first construct the rationals, and then perhaps the transcendentals, and then once we have the transcendentals and the rationals, we put them all together, or we union them with the integers and the naturals, and then we get the real numbers. Now, of course, we don't have to worry about getting duplicate copies of numbers, because once we have two copies of one object in a set, they sort of just absorb into one element. Just like how, you know, sets really, you know, a fundamental rule of sets is that any repeated element is just, you know, just that element. So, yeah. So there's total ordering for you. Okay, so that's our isomorphism. Now, let's carry this on over now to a more specific case, which is the Femboy. So, the same procedure applies for when we talk about Femboys. So, this time I have an indexed family of Femboys, f sub I, and our L just simply takes f sub I to a corresponding I in J, I indexed by set J. And of course, cardinality of J is precisely n. Okay, so it's simple. Every Femboy is given a label or a number, just like how every person or subset of, you know, the power set of math BFC, or the power set of all possible human characteristics. Every subset of that, you know, we can correspond to a number. We can correspond every Femboy to a number. Of course, now Fi this time is just an element of not mathcal math bold C, or mathcal of math bold C, but rather f sub I is an element of the space of all femboys, or the set of the fundamental or the universal set of all femboys. It could be a set, it can be it can be a space, but we mostly entertain this as a set, especially in these things. Okay, so now that we have some notion, we have one more thing. Oh no, that's it. Okay, so now I'm gonna give you guys the full sketch of the commutative diagram between this, F, its cyclic group of order n, or not the cyclic group of order n, but rather its F mod n, and we're also gonna include in there Z mod n and then Z and F themselves. Okay, so I have F, I have the integers, I have F mod n, and then I have Z mod n. And then we have this following, these following maps. Now, I'm gonna leave it to you guys as an exercise to determine whether this commutes or not. Okay, I'm gonna leave it to you guys as an exercise that if it commutes or not. Like we can go from here to here. So if I take an element here to here and then do this element to here, it's just the same as going straight from F to here. That's what commutes means, and that will work for everything here in this diagram, following the arrows, of course. Okay, so F to Z is L. That is our isomorphism. Now the thing is, this is only for the underlying set, so I'm gonna label this as asterisk. This is not the L that we know and love just yet, because we haven't, discussed about carrying over the notion of addition. Now, how do we correspond, or what is our corresponding notion of addition here? I mean, we don't know just yet how the hell we're gonna add the femboys, because we don't have a concrete notion of what femboys are just yet. Femboys are an abstract object. But I will show you guys that it is quite trivial to actually add femboys, because if we are able to correspond them, or say that there is an isomorphism with them, right? We already identified an isomorphism, or an equivalence between, or at least a relation between the set, the underlying sets. Surely we would be able to carry on over some structure from one set to the other if we add that structure or take into consideration the structure of the set. So I'm just gonna label this L here as a star now, for now, because this entire diagram implies a different diagram which involves the actual groups themselves. Okay? So, alright, so this is L. And then this here is mapped onto here via some isomorphism. Or not really isomorphism, but is some new relation which I will call not really L, some other I know this is here somewhere. Yeah, parallel here. Okay, I'm just gonna use C letters. So let's call this P, it's C, and then, or no, this is, C, and then this is, mathcal Z. Okay. And these are all star, obviously, because the actual mappings take the groups, or make a homomorphism, or are homomorphisms between the groups, or isomorphisms between the groups. So this commutative diagram implies this commutative diagram. With addition operation taken to additive group of the integers via L itself, and this additive group is taken to this additive group, so F mod F, or mod N, and then addition, and then we take that to Z mod N, and then addition, and then we take that to Z. Okay, and then this is precisely mathcal Z, This is precisely math cal P, and this is precisely math cal C. Now I can use the curve C here, so it's not confused. Okay. So this diagram here implies that we also carry over structure from the groups. Or so if we consider not only the underlying set but also the operation, there's some notion. Now you may be thinking that this is unjustified, that it's that I cannot necessarily say this yet, but you're only saying that because I have not yet identified the isomorphism or the analog of this operation in this set. So the analog of this operation with respect to the fundamental set of all femboys. And actually that correspondence is quite trivial. It's easy to show that. And likewise, because because the structure here works, or the structure here is isomorphic, I will show you guys. Because these two are, because these two structures are isomorphic, we know that when we do construct something out of this group, it could also, it has some corresponding isomorphism with this over here. So to speak, L and P are somewhat similar, If we think of these as categories, we can say that there is I suppose, a natural transformation between L and P. Now, for the category theoretic viewpoint of all of this, I will show you guys later, right at the end of the lecture. Okay, so let's construct that equivalence or that relation between this addition with respect to the integers and this addition with respect to the femboys. Now there are many ways of corresponding or making analogs of addition with respect to the integers, with respect to the additive group of integers, our intuitive notion of adding integers, and corresponding it with adding femboys here. One way of thinking about it, at least, is one way of thinking about this. So I'm gonna erase this left part because we copied it, but I'm gonna keep this on. Now one way of thinking about it is if we think of F here as a space, as a vector space, well, we just add the vectors, just add the magnitudes of the vectors or the components of the vectors piecewise or point component wise. So if I have Z2 here and I have F2 with addition, still a group by the way. I'm assuming that every femboy has this corresponding inverse that, such that when you add them together, they disappear. So I have a negative version and I have a positive version. But that is not to imply that the negative version is strictly less than or beneath or not as superior as the positive one. That is not to imply, or that this doesn't imply that notion. Okay, we're just mathematically playful with this stuff. Okay, so all right. So I have a femboy here that can be expressed as the linear combination, or as a linear combination of the base states, or base femboy states, which let's assume since we're basing our theory off of position theory, let's say that our basis is the top and the bottom states. Okay. So alpha, some constant alpha, or scalar alpha times the top state plus beta times the bottom state. Now, if the femboy is a bottom, of course, alpha would be set to 0 and beta set to some magnitude. If they are strictly a top, then alpha over here would be set to some arbitrary value, and the beta would be set to 0 if they are somewhat an analog of both of them, or somewhat a combination of both of them, like say a switch. Now, of course, none of these guys are both alpha and beta are non-zero values. Okay. So, right. This is one way of thinking about, addition of these two. Like how if I have two coordinates in Z2 here, I have a vector in Z2, I will express it via array. So I have AB. And then I want to, I can express AB as some linear combination, right? Linear combination of A times the basis vector 0, 1 plus B times the basis vector 1, 0. I can do that. And in fact, this are all very similar. This is extremely similar to this. It's just notation that makes it look different. When in fact, we know that, these are just bases for this one here, and then these are bases for this. I'm assuming this is our basis. Okay, I hat and j hat. The conventional, at least according to linear algebra, the conventional way of expressing them. Okay. So that's one way of thinking of similarities between these two. Or we can think of in terms of points. So not vectors, but let's express Femboys as a point. I mean, no, vectors are technically points, but points like exclude like that line that leads from the origin to that point. But if we think of them in a point perspective, we have some point or some Femboy point fx and then fy, and then we have a point in z2, which is x, y. Of course, both of these values are integers. Okay, so I want to add these two to a different, thing. So f ab. So, like how I will add this to some other coordinate ab, which is we just add them component-wise. So fx is fa, comma, fy plus fb. And then likewise here, a plus x, y plus b. And that's at least the relation between them. That if we have, of course, our ordered pairs from these two structures, adding two ordered pairs would just be simply adding them component-wise. So that is the relation between these two additions here. Now, if we only have one component, you just add those components together. And because we have an isomorphism between this and this, we don't have to worry much about, the actual, nature of the addition. It's as intuitive as it comes. Because under L star, or L sub asterisk, some Femboy f sub I corresponding to the integer I here. If I make a change here to this I, I'll call it delta I, plus some change delta I, there will be a corresponding change here. So there will be a corresponding plus delta fi. Wherein that corresponding change is only just, it's influenced by how this changes. So if I add some constant to I here, there will be some corresponding change to to this here. So it's a similar notion. So let's say for example, I have a Femboy f1. Of course, its corresponding component or element in the integers is precisely 1, right? So it's corresponding to that under L sub asterisk. Now, suppose I want to add this Femboy and another Femboy. And then, okay, I have another one, F2, which corresponds to, under this same mapping, L sub asterisk, or mathematical L sub asterisk. Now, let's say I want to add F1 and F2. Now, because these two are equivalent to 1 and 2 respectively under mathematical L sub asterisk, we can draw conclusions from adding these two. So 1 plus 2 is just 3. We know that. Simple notion, proven via the natural numbers. Of course, we'll just prove these results, or we've already proven these results in foundations. So, okay, so we want to find some mystery Femboy here. Now, obviously, we know that 1 corresponds to F1, 2 corresponds to F2. So, you guys already know the pattern from here. What Femboy is correspondent to 3? That's F3, obviously. Because we already established a while ago that every F sub I, or Femboy, indexed by I, is corresponded to some integer I. That is the fundamental law of L here. of our mapping or our isomorphism between these two sets or these two structures. So there it is. So this is the one that I want you guys to focus on. This is the operation that I want you guys to focus on. Now, I think if you guys would want to in your free time, maybe you can try to find other notions or analogs of addition that carries over from an isomorphism between Z and the femboy space or the universal femboy space. So there's our isomorphism. And now likewise, if I have some cyclic group, cyclic group. These are technically cyclic groups, right? Or integer cyclic group or femboy cyclic group. No, I'll show it's equivalent to a cyclic group or isomorphic to a cyclic group later. Okay, so this one over here also carries the same notion of addition. It's just a derivative of the structure, not the literal derivative in the calculus sense, but rather derivative wherein we derived it from this structure. Like we constructed it from this structure. Okay? So now, don't be confused by this notation. I'm just borrowing notation from Z mod n. Okay. All right. Oops. Let's show some isomorphism between these two. Okay. So under C here, C is just our construction of this. Well, we just carry on over the operation. So we take the fundamental set of all femboys, right? And then we slash off at the nth femboy, and then we tell it, or we give it the law that when we get to the nth femboy, we wrap back to the zero femboy, okay, or the empty femboy, or the empty person in the case of the fundamental space of all persons, or mathcal P of math BFC. Like how when we construct integers mod n, all we do is just cut it at the nth integer and then say that once we get to the nth integer, we wrap back to zero. Okay, so this set, I'll denote zero as the zero femboy. No ambiguity here. What we just say for now is that zero femboy here, let's say, is a it is both a masculine and a feminine femboy. No, femboy is inherently feminine or intrinsically feminine. So being feminine is an intrinsic structure for an element of it. Okay, let's say likes both girls and boys. So they are bisexual, let's say. Zero denotes that. So this is ranging over all of P. P. This P, in O course P, if you remember that notion. Okay, so 0 and then femboy 1, which we will denote F1, F2, let's say up to F3 and F4. So these are the first 4 femboys of the fundamental set of all femboys. These can be interchanged and all that, but just for the sake of convenience, we're going to order them in ascending order and using these numbers. And also because of our intrinsic rule for mathcal L's sub asterisk or underscore sub asterisk or underscore asterisk. Okay, so this set becomes, under C, our construction, it becomes the same set, but we just extract 4 from it. And this is essentially over here. This is just F, the first 4 of at least. First 4, and it is taken precisely. Yeah, this is the image after all. Or no. It is taken precisely to F mod 4. So this is precisely F mod 4. And we just say that for n equals 4, Fn equals 0. or some multiple of 4, right? Now the fifth femboy, right? The fourth femboy is 0, right? Fifth femboy is just congruent to the first femboy, modulo 4. So one thing to note here is that, for example, F5 is congruent to F1 mod 4. Now you may be thinking, oh well, this is an integer. It's not strictly a femboy. What the hell do we say mod here? So we don't say mod 4 precisely, but we say mod F4. Okay. So this doesn't intrinsically say mod 4 exactly, but this implies mod F sub 4. So mod the fourth femboy. So I know it's a bit of a mouthful, but it gives the precise, description of what this string is. So it is F mod the fourth femboy. There. Answer C, and then we just take out 4 and then give this. We say this structure here, or this sort of rule, I guess. Okay. And all right. So that's our C. How about our assignment of each of these guys? Of course, our L here. I mean, this is just the underlying set. So this is L star, and this is C star. Okay. So L star give us just 0, 1, 2, 3, 4. And then, 0 is just corresponding to 0. So this could be a symbol for a femboy, but under the integers, this is 0. Okay, which so happens to be neatly represented as nothing of something, no amounts of something. Okay. Okay, that's carried over. These are all images, so we use maps too. This is the same diagram as this, but we just flipped it over in a weird way. So this is taken to its modulo, let's say 4 also. So under mathcal Z becomes 0, 1, 2, 3. And then where's mapping over here? And that is just P. And then, operation of addition carries on over. Yeah. So that's one example at least. So this is for the case F mod 4, or the fourth femboy, and Z mod 4. Okay, now that we've talked about this diagram over here, this commutative diagram. Again, exercise to prove this. Let's talk about cyclic groups. So what precisely are cyclic groups? No, we've discussed like certain groups here. We've discussed the multiplicative group. We've also discussed the additive group. The subtractive group and the division group are different stories. They're simply just the inverses of addition and multiplication respectively. So we don't really need to discuss about them, because their existence and the proof for their existence is already justified or is already covered by showing that their respective additive and multiplicative groups exist. Okay. So let's talk about cyclic groups. Now that we are equipped with knowledge and the intuition behind modular arithmetic, let's talk about cyclic groups. So a cyclic group is a group that's generated. It's a group generated by one element. So cyclic groups usually have underlying sets that contain, of course, the null set or our identity element. Null set can be thought of as our identity element, and then we have our element R, and then R squared, R cubed, and on and on. The trivial cyclic group is just R. This is the trivial cyclic group, C1. C0 is just this over here, just the empty set. Now, these things are denoted via their order. So a cyclic group Cn contains, n amounts of generators. Aside, n plus 1 amount of generators actually, because we have our empty set. But actually, no, let's not use the empty set. To make it more intuitive, let's use an identity element, which we will call E. Okay. E is our identity element. So a fundamental rule of E is that for some R multiplied by enough times, wraps such that it wraps back to E. So let's say I have a cyclic group of order 3. Let's say I have C3, which is E, R1, R1, R2, and R23. Of course, you guys already know at this point, because it's cyclic, from the name, it must be that it wraps back to E. So it gives us a notion of closeness. Now the problem with cyclic groups is that we don't quite have inverses here. So how the hell is it a group if it doesn't have an inverse? Yeah. How the hell does it have a group if it doesn't have? How the hell is it a group if it isn't? If every of these guys don't have an inverse? Now, the inverse of every element is basically just composing them until we wrap back to E. So I know this is a bit hard to wrap your head around, but the inverse of 1 is R1, R2, R3, R4, which is just E. So the inverse of some R1 is R1, R2, R3. Because when we apply this, we go R1, so we go here, and R2, go there, and then compose again with R3. We wrap back to E, precisely E. Because we know that an inverse, actually inverse is R2, R3. Because we know that for any element A, and its inverse A to the minus 1, A composed with A to the minus 1 is equal to A to the minus 1 composed with A. It's just an identity element. That's the group law for an identity element. So really, we don't need an R to the minus 1 because composing R with, the elements after them, traveling along, let's say this is a line, right? Traveling along that line or along that circle, is already enough for us to wrap back to E. It's like if I have a Rubik's Cube and then I rotate a side, let's say L, I rotate it 1, 2, 3, 4 times, it wraps back to as if I didn't do anything. So although I can make inverse moves, although I could make an inverse L move, like L to the minus 1, or R, I think, or L prime, L prime. If I do L prime, it's just the same as, L, L 3L or L plus LLL mod L4 or mod 4 or whatever your notion of the fourth move is. Okay. So the point is we don't need to actually show, or we don't need that there are actual inverses here that they, multiplicatively cancel out. Because this is a cyclic group and it follows the rules of modular arithmetic, it wraps back to an identity element. We just need to keep multiplying it until it wraps back. So that's why we don't necessarily need inverses like to the minus 1, to the minus 2, to the minus 3. Okay? So, right, this is a cyclic group. Of course, its operation is obviously composition. Its underlying set is something that looks like this. Now, you may be thinking, okay, how the hell does a cyclic group correspond to Z mod n? You already know, you see the structure carries on over, that's trivial. But how do we show that each of these guys is, it's sort of, how do we show that Z mod n is precisely a cyclic group. I mean, every element is sort of like, it's already there. They have their own additive inverse. But here's what I'm gonna tell you guys. What if, instead of thinking all of these numbers as the entire set, what if we think of it as just, you know, all of these guys, but mod 1. Mod 1. Okay? Hear me out on this. What if, instead of thinking as Z as, you know, 0, 1, 2, 3, 4, 5, 6, on and on and on, let's restrict it to the positive integers just for the moment. What if I were to say that instead it is 0, okay, 0 mod 1, 1 mod 1, 2 sorry, that's not how you express it. 0 mod 1, 2, 3, 4, 5, and then on and on and on. Okay, yeah. 0 and then 0 mod 1, 0 mod 2, 0 mod 3, and on. Now this looks strangely familiar. This looks strangely familiar to E, R1, R2, R3, and on and on. Huh. So now you guys see. Now if I restrict it to only, let's just restrict it to Z mod 7. Z mod and then 7 and then Z. So this would entail, or we would want a cyclic group of order 7. So C7. This here is supposedly equivalent to C7. Well, C7 is some operation, and then we have the set E, R1, R2, up to R7. So what is the isomorphism between, you know, each of these R to the I and, you know, integers? So just like how every F sub I is corresponded to an integer I, what we do is just set this one, or let's grab one of these guys. Let's grab an R, and let's name it R sub R to the I. And then let's correspond it to some 0 mod I. Or not really that, but it's I, some I mod 7. And there it is. Just like how we corresponded each femboy to an element of, you know, this cyclic group, you know, mod integers mod 7 or mod n, we're able to correspond this cyclic group to every element here. Because well, I'm gonna show you guys now, or I'm gonna show you guys that this is a bijection because every element has something to map onto. I'm gonna use addition operation. Now the addition operation carries on over, or the structure, you know, composition and or concatenation. This looks like concatenation. It's just concatenation, string concatenation. It's somewhat similar to addition in the way we travel along an imaginary line, like a line you construct in your head. Like imagine a line, and then every element is listed on that line. We travel along that line and then wrap back to 0. In the same way, addition here makes us go one step closer and then wrap back to 0. The 0 is our identity element. So it's addition and then 0, 1, 2, 3, 4, ... I'm gonna make it more compact and say just 2 and then ... up to 7. This is an isomorphism. An isomorphism is inherently a bijection. And this is a bijection because every element here, it's a one-to-one mapping. Although you can say, oh, you can define R2 to be equal to R3 under some new law that isn't inherently math cal L sub asterisk. Okay, But ultimately, if you guys map onto a corresponding element and no other element is left behind. So it's amazing, truly amazing that we're able to correspond these two. And because we're able to correspond this cyclic group of order 70 here, since we have shown that there's an isomorphism between this cyclic group and this cyclic group, so I'm just gonna, we can show thus that this carries on over. So I'm going to take a step further and say, in the big picture, or in the big picture of it all, this operation of corresponding or making isomorphisms between these cyclic groups is transitive. That because we are able to make an isomorphism between this cyclic group and this cyclic group, we can make a direct correspondence between this cyclic group and F mod n, mod the nth femboy. So C7, so here's our theorem now. Here's our theorem. I'm gonna erase this. So keep this relation in mind, or keep this these two strings in mind, or that relation I wrote here a while ago. Theorem. C7, Cn. So that's not how you denote the cyclic groups. Cn is isomorphic to F mod the nth femboy. Okay, we have already shown that the integers mod n, or the integers, is isomorphic to F because every femboy has a corresponding integer, and we will never run out of integers. We are not saying that that z is uncountably infinite, and because these two have technically the same cardinalities, we have a bijection. Okay? Only when one set is bigger than the other do we have something that isn't a bijection. Okay, so proof. Cn is isomorphic to Z mod n. Well, additive group at least. So this with addition. And since Z mod n is isomorphic to F mod the nth femboy, it carries on over that Cn is isomorphic to F mod the nth femboy addition. QED. I don't know. Yeah, QED. Or box. How knows? So yeah, I know this has been like a little bit of a heavy lecture, but this is ultimately a wonderful result that we came up with here at LOSC. So yeah. So I believe the next lecture would be something first that I would be making position theory about tensor sums and tensor products, and also the fact that Fn tensor product Fm gives us an F space of n times m dimensions, and then the direct product between F to the n and F to the m gives us a space F of n plus m dimensions. And I'm gonna sort of demystify the tensor product and the tensor sum, because just today I learned about a very intuitive and very easy way of thinking of these guys aside just bijective math, because usually these guys are this is side lecture, okay? This has nothing to do with the lecture that I just did. Usually these guys are expressed as some bilinear map that takes two vector spaces V cross W and takes them to V O cross W. And likewise, the direct sum takes V cross W and takes them to V direct sum W. It's unintuitive. what they don't give us is what it does exactly to a vector from V and to a vector from W. So by position theory, we are gonna go into that. Okay, and I don't think it would be I don't think it would be very long. Maybe it would just be 15 minutes or 30 minutes long. I would try my best to flesh up this topic as best as I can in position theory. And it's really good. It feels good to revisit some of these concepts and actually continue building the theories that I've built before, even though I've already completed the course. So we're already a bit slightly over time by 5 minutes, and this is a good place to stop.